everybody, I just wanted to take a little bit of time and give you maybe the nickel tour of gas chromatography. This is not designed to be an in-depth look at how gas chromatography works, but more like a primer in what kind of information you can get from it if you were, let's say, in a lab class. So let's talk a little bit about gas chromatography, or what we call in the business GC. So here we go. So let's keep in mind that GC is a way, just like all chromatography, to separate things. And so we're going to be using gas to separate these mixtures. And so typically when the mixture is separated, it separates based on kind of three different things. So boiling point, size, and what we call affinity to the column. And I spelled affinity there incorrectly. I'll make sure I change that if I link the slideshow to this. But the idea here is, as you have a mixture, and typically it's a liquid mixture, but it can be a mixture with solids dissolved in it, or it can be a gas mixture itself. You're going to have that mixture and you're going to turn it into a gas, and then you're going to push it through a very, 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 very small diameter column. And as that small diameter column, as the mixture travels through it, it's going to separate, because those compounds are going to interact with the column a little bit different, because they may be bigger, and they may be bigger things are going to travel slower through it. It may have a different boiling point, which will affect how it travels, or it could actually interact with the column in just a whole different way than other compounds in the mixture. And so one of the reasons why we use GC is because it's pretty versatile. It can be used in a lot of different situations. Actually, one of the things that they can do very quickly is to take a GC sample to figure out if people, not people, but if samples of things have different types of drugs in it. The readout of a GC is going to give you one peak for every one compound that's in the mixture. So if you have a pure compound, it'll have one peak. If you have a mixture that has two compounds in it, it will have two peaks on down the line. So state police labs use GC to determine if a drug, an illegal drug, is pure, or if it's mixed with a whole bunch of other things. And it's good also because in general it's pretty accurate. So here's a little, and I know that it's blurry, but here's how a GC works. So you have what they call a carrier gas. So the gas is going to push the sample through the column here, okay? If I were to just inject the sample here, it would just sit here in the injector and not do anything. The gas will push it through the column. And again, this column is very, 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 very small in diameter. So you're really only having a few, maybe a few micrometers of width of compound going through the column at once. So you don't really need much in the way of a sample to do GC. And so the injector will turn your sample into a gas, and when it's a gas, and again it's being pushed through some sort of inert gas like nitrogen or helium. Helium is the best one to use, I think. It'll push through the column, and as it travels through the column, the slow molecules, the ones that are big and attracted to the column, will go slowly through the column, and the really quick ones will run a race and run right through this column really quickly. And so then eventually they will come out to the other side. So the ones that were very fast will come out first, and the ones that were very slow because of their size and the way they interacted with the column will come out last. And then you get a readout. And so on the readout, you'll see the size of the peak up and down, and then you'll see what we call retention time, or how long it was in the column. So those are the two things that you can that you'll get when you get a GC. So I think to explain this, I think it's good to just look at a couple of GCs. Some are fake, some are real, but that way you can kind of see what the heck is going on. Okay, so here we have an example. We have 3 different mixtures, and the mixture is that of octane and nonane. Okay, now the difference between these is just 1 carbon, but this is where nonane, being bigger, will travel through the column more slowly. Okay, so you can see on the axis here on the bottom, this is what we call retention time. And so what we have here, just to make sure that we're clear, is we have 3 different GCs. We have this one, and this one. So the 3 different GCs represent 3 different mixtures, and so we injected mixture 1 into the GC, and we get this. So we can see that it comes out with 2 peaks. Now, we wouldn't know if the peak is octane and nonane, but what we do know is that that mixture was injected into the column, so the one that comes out of the column first is the one that is smaller, the one that races through the column more quickly, the one that is less interactive with the column itself. And so you get octane first, and then nonane will come out second because it's bigger, it interacts with the column, or it has a higher boiling point, so it's going to come out of the column second. And so that's how we know the order with which things come out of the column. We call that elution order. Okay, so octane will come out first, nonane will come out second, and that's true with mixture 2 and in mixture 3. We see octane coming out first in all 3 of these compounds. The second piece of information you get from this is the height of the column, or probably more importantly, the area under the curve. Now, when I was in school, and I had to do GC, we actually had to calculate area under the curve, and that was a pain in the neck. But here we have high-tech GCs that will calculate that area for you. But here, what we want to do is just make some generalizations about each of these things. Okay, you'll notice that the area under the curve, or the height of this octane peak, is smaller than the height of the nonane peak. What that means is that this mixture has less octane and more nonane in it. Okay, it's less octane and it's than nonane. Now, if you were to actually calculate the peak, or the area under the curve, you would be able to get an exact percentage of how much octane is in this and how much nonane is in this based on the areas under the curve. Okay, so now we go here to mixture 2, and again, you see octane first because it's going to be the first out of the column, and now you see that octane is in a greater percentage here, and nonane is in the least percentage. It's coming out smaller. And now in mixture 3, what you can see is they're coming out at exactly the same height. So this means that this mixture here is exactly 50% of each compound. That is a piece of information that you can get from the GC. Okay. So now in the second example, here we talk again about the area and what the meaning of the area is. Okay, so this is again a mixture of 2 things. You're going to get ethanol here first, coming out first, and 1 propanol coming out second. And again, we look at the boiling points here to give you an idea of what's going to come out of the column first, which is going to race through the column more quickly. Based on boiling point. In terms of polarity, these 2 are probably a little bit probably similar in polarity, but you can see that ethanol is also maybe a smaller compound by molar mass. But the point here, other than retention time, is that this area under the curve, if you were to calculate it, this is about 2 times that of propanol, 1 propanol. And so the information here says that if this is twice that, this is going to be 67% ethanol and 33% propanol. That's the information that the GC will give you. So now let's look at an actual GC. Okay, and I apologize for its blurriness, but I'll make sure that I do this. If we look here, we can see that the GC has several peaks that are identified. Okay, and what's going to happen is the peaks are all going to be printed out with the time it took for them to go through the column. And so in this case, we have 1, 2, 3, 4, 5, 6, and then there's one behind this thing, 7 compounds. And it then calculates the area under each of these peaks, and then it'll determine the percentage. The area percent is literally the percentage of the compound in the mixture. Now that can change slightly based on the mixture that you're running, but in general, that's a great rule. So what we're saying is that this first peak, the area is 72.84%, but that means that that mixture is 72.84% of whatever that compound is. Now they've come over here and they've identified that first compound as vitamin A. And then there's some other smaller compounds, but then you come down here, the compound that comes out at 20.8 minutes is 19.57% of the total area. Okay, well, that means that mixture is probably 19.57% of that compound. And then they come over here and they've identified that compound as vitamin E. So there's some of these that are very small. If you get something that's super small, sometimes those are not meaningless, but it's such a small number that it doesn't that we don't really count those. So when you get data from a GC, you're going to look at this percentage, and that percentage is going to tell you how much of the compound is in the mixture. And then the retention time also can give you a little bit of an idea of what the identity of the compound is. Okay, so knowing that polar compounds are going to come out a little more slowly, smaller compounds come out a little more quickly, and things with lower boiling point are also going to come out a little more quickly. So that's your little lab primer on GC and what kind of GC is used for. So hopefully this will help you in identifying some GC information in your own labs. Have a great day, everybody.